All right, Merry Christmas. I thought about doing a Christmas special, like a special video, maybe like I don't know, some kind of Christmas related programming visualization thing. But no, I didn't do that. Today, we're just going to be doing Advent of Code Day 25. So, this is going to be the end of the series for Advent of Code 2020. There will be more next year, but that's it for this year. So, Merry Christmas, and today we're going to be doing Day 25 of Advent of Code. Hope this is fun and it brings some Christmas spirit. All right, Day 25, Combo Breaker. You finally reached the check-in desk. Unfortunately, their registration systems are currently offline and they cannot check you in. Noticing the look on your face, they quickly add that tech support is already on the way. They even created all the room keys this morning. You can take yours now and give them your room deposit once the registration system comes back online. The room key is a small RFID card. Your room is on the 25th floor and the elevators are also temporarily out of service, so it takes what little energy you have left to even climb the stairs and navigate the halls. You finally reach the door to your room, swipe your card, and beep, the light turns red. Examining the card more closely, you discover a phone number for tech support. Hello, how can we help you today? You explain the situation. Well, it sounds like the card isn't sending the right command to unlock the door. If you want to, if you go back to the check-in desk, surely someone there can reset it for you. Still catching your breath, you describe the status of the elevator and the exact number of stairs you just had to climb. I see. Well, your only other option would be to reverse engineer the cryptographic handshake the card does with the door and then inject your own commands into the data stream, but that's definitely impossible. You thank them for their time. Unfortunately for the door, you know a thing or two about cryptographic handshakes. The handshake used by the card in the door involves an operation that transforms a subject number. To transform a subject number, start with the value 1. Then, a number of times called the loop size, perform the following steps. Set the value to itself multiplied by the subject number. Set the value to the remainder after dividing the value by 20201227. So, the card always uses a specific secret loop size when it transforms a subject number. The door always uses a different secret loop size. So essentially what we're doing here is we are just raising the subject number to the power of the loop size. Because notice we're multiplying the value 1 by the subject number loop size number of times. And then we're going to take all of that modulo 20201227 because after every time we exponentiate, we're taking it mod 2021-227, which basically just means taking the remainder after dividing by this number. And I'm just going to call that mod, I guess, just so I don't have to say that 8-digit number again. So we're basically doing subject number to the power of loop size mod modulo, okay? And that's basically what transforming a subject number means. The cryptographic handshake works like this. The card transforms the subject number of 7 according to the card's secret loop size. This result is called the card's public key. So we're doing 7 to the power of card loop size. The door transforms the subject number of 7 according to the door's secret loop size. The result is called the door's public key. The card and the door use a wireless RFID signal to transmit the two public keys, your puzzle input, to the other device. Now the card has the door's public key and the door has the card's public key. Because you can eavesdrop on the signal, you have both public keys, but neither device's loop size. The card transforms the subject number of the door's public key according to the card's loop size. This result is called the encryption key. So basically, we're doing card public key to the power of door loop size, and door public key to the power of card loop size. That's what these two steps are, and they result in the same number, and I can explain why later. If you can use the two public keys to determine each device's loop size, you will have enough information to calculate the secret encryption key that the card and the door use to communicate. This will let you send the unlock command directly to the door. For example, suppose you know that the card's public key is this. With a little trial and error, you can work out that the card's loop size must be 8 because transforming the initial number of 7 with a loop size of 8 produces that number. Then suppose you know that the door's public key is this. By the same process, you can determine that the door's loop size is 11. At this point, you can use either device's loop size with the other device's public key to calculate the encryption key. Transforming the subject number of this with the loop size of 8 produces the encryption key. Doing that with the card public key and the door's loop size produces the same encryption key. What encryption key is the handshake trying to establish? Okay, so this is pretty good. I think we can tackle this pretty easily. So I will explain this after I solve it. So I'll see you in a few seconds. Okay, so that took a little bit of time, but we have our answer. It only took maybe 10 seconds or so that's the right answer. Okay, let's explain. This will require a little bit of drawing. So if you know a thing or two about cryptography, you know that this is basically the Diffie-Hellman key exchange. Maybe a little bit simplified, but this is the basics of the Diffie-Hellman key exchange. How it works in this example, I guess, we would have a generator of 7. Generator, it doesn't really matter what the generator is. So we have a value of 7. We raise it to the power of card loop size. We'll just call that we'll call that A. We'll call that L. We'll call that L. And then we take that modulo 2020 1227. So this is how you transform a number. Sorry, no. We need to. Sorry, I got this notation wrong. Modulo this number. This is how you transform a loop size into, well, a subject number and a loop size into the result. So this is what the transformation is, because basically we're repeating this loop size number of times, and loop size is L, so this is loop size. We're multiplying the value 1 by 7, and then we're multiplying by 7 again, and then we're multiplying 7 again, and then we're doing that until we get to loop size. Yeah, basically that's it. This is how we transform a number. So we have, let's call the card's loop size C, and let's call the door's loop size D. So we have 7 to the power of C mod, let's just call this M, big M, where M is equal to 2020 1227. Okay, because I don't want to write this number out every time. So this is the card's public encryption key. Card public key, okay? And then the door's public key is 7 to the D mod M. Now, we don't know these loop sizes, so these are the loop sizes. And we're not supposed to know them. They're supposed to be secret. So this is going to be the door's public key. And then after we do that, these get exchanged. So we now know what these are. We know 7 to the C mod M and 7 to the D mod M. Now, how do we actually... well, actually, no. There's one step that happens after this. Card's public key gets transformed by the door's public key. So we raise this to the power of D, and this is actually equivalent to 7 to the C to the power of D mod M. This is a little bit of modular arithmetic for you. It's pretty interesting. So this notation just basically means two numbers have the same remainder when divided by M. If we put like X is equivalent to this, that means these two have the same remainder when divided by M. Okay, so now the door has this common encryption key. I can't write today. Okay, this is the card's encryption key. No, this is the shared encryption key. Then the door's public key gets sent to the card. The card does 7 to the D to the power of C mod M, and this is mod M. So this is what the card has, and then the card has this equal to 7 to the DC, which is actually equivalent to 7 to the CD mod M. So you can see that these two numbers are the same. So these two numbers do have the same encryption key using the process because of the process I just described there. And now we actually have to like bash this out. So we have to find out. So we know this. We know 7 to the C mod M, and we know 7 to the D mod M. We also know that this is 7. We also know what M is. So what we have to do is basically just bash it out. So I made this function called find loop size given a subject number and a public key. Our subject number is just 7. That's what the problem tells us. The subject number is just 7. The public key is this number over here. So this is the card's public key. We'll just work with the card's public key. Sorry for that. But okay. I want to write something. Okay. So this is what am I doing? Okay, so we have access to the card's public key, as well as the number 7, and that's what gets inputted to this function over here. Now we need to find C. So this is what we need to find. Okay, we need to find C. So we basically just bash it out. We try every exponent in from 1 all the way to m. So we try all these exponents, and we see which one works. Or we actually don't have to put a cap at m, but using some mathematical proof, you can prove that the highest possible number is actually m minus 1. That's the highest possible exponent because after that it starts repeating. So we know that we just go through all possible exponents, all possible values of c, and if we raise subject number to the power of this possible loop size and take it modulo m, Python actually has this great like built-in function that lets you compute powers like modulo a mod, because there's some optimization that you can do with it. I don't know what it is, but you can do some optimization to make it run faster. So if we transform subject number with a loop size of I by raising it to the power of I and then taking it mod, if the transform number is equal to the public key, then we have found our loop size or exponent. So we can just return the loop size or exponent. That's that. Otherwise, if we don't find it inside a certain range, then we can turn -1. But it's always guaranteed to be in there if the input data is valid. So we find our card public key and our door public key. It doesn't have to be in that order, but that's just how we get the input. We split the input by new line, and then we get the 0 and first elements and turn it into integers. We find the card loop size by calling this function on a subject number of 7 and the card's public key. And that's how we find the loop size. So then we just transform. So once we have C, we also know this number, so we can just raise that to the power of C. And this is going to get us the encryption key. So that's what we output over here. It takes a little bit of time to run, but that's fine. That's fine. It only took about 10 seconds for me. All right, part 2. The light turns green and the door unlocks. As you collapse onto the bed in your room, your paper goes off. Your pager goes off. It's an emergency, the elf calling you explains. The soft serve machine in the cafeteria on sub-basement 7 just failed, and you're the only one that knows how to fix it. We've already dispatched a reindeer to your location to pick you up. You hear the sound of hooves landing on your balcony. The reindeer carefully explores the contents of your room while you figure out how you're going to pay the 50 stars you owe to the resort before you leave. Noticing that you look concerned, the reindeer wanders over to you. You see that it's carrying a small pouch. Sorry for the trouble, a note in the pouch reads. Sitting at the bottom of the pouch is a gold coin with a little picture of a starfish on it. Looks like you only needed 49 stars after all. You have enough stars to pay the deposit. Okay, that's great. So, looks like we didn't need to do another puzzle to get another star, but looks like we're going to have to go back to the North Pole for a little trip to fix the soft serve machine. So, should we pay the deposit? Let's do it. Okay, you spent all 50 stars to cover the room deposit. As you fix the soft serve machine, Santa offers you a ride in his sleigh. Maybe the resort has a chimney you can use. Yay! We finished every puzzle in Advent of Code 2020. Let's just read this. I hope you had as much fun solving them as I had making them for you. I certainly did. I'd love to hear about your adventure. You can get in touch with me via contact info on my website or through Twitter. It's fine. If you'd like to see more things like this in the future, please consider supporting Advent of Code and sharing it with others. I think this is great, but I don't have any money. So to make me earn money, please consider supporting my channel. And let's get to 1,000 subscribers and 4,000 public watch hours. And then I can start earning money. All right. To hear about future projects, you can follow me on Twitter. I've highlighted the Easter eggs in each puzzle just in case you missed any. Oh, okay, let's take a look at the Easter eggs. Okay, hover your mouse over them and the Easter egg will appear. Whoa, okay, I didn't know there were Easter eggs in here. Whoa, wait. What's this? What's this? What's that? I don't know. What? Wait, alright, I don't understand what this is. So this is bonus content right here. If you want to leave, you can leave right now. Dang, okay, the sea monster moves. Wait, oh, I think this was the storm. This is the storm that. Okay, that's pretty cool. Alright, first day. Surely. Yeah. Surely, what could go wrong? Okay, that's pretty good. You know, maybe I'll put the Easter eggs in a separate video just to make this a little bit easier. Okay. I'll review the Easter eggs in a different video. But so that's it for today. Thank you for watching. It's been an epic ride throughout this month. I hope your Christmas goes well if you want to celebrate Christmas. But yeah, have a nice day, and I'll see you hopefully soon. Maybe with a New Year celebration video or a Yusuka video. Depends. All right. So thank you for watching, and I'll see you not tomorrow. Later. Goodbye. Thanks for watching.